Kavita madam joined,
Sir.
Joined here. That will start now. 2
Yes,
minutes
sir.
will start. Sir, shall we start, sir? Puli Kishore, sir.
Yes, sir. Very good evening, sir. I'm here. I'm just trying to request you to share my screen.
I will do it, sir. Kavita madam, you can do it, madam.
Yes, sir.
Yeah.
Good evening to one and all. I, Kavita, Assistant Professor, Department of PCA. Welcome to all the participants of Atal FDP Session 8 by Dr. Puli Kishore Kumar, sir. It's my privilege to introduce our today's speaker, Dr. Puli Kishore Kumar, sir. He completed his BTech from Yale University in 2006 and MTech from Yale University in 2008. PhD in radio signal processing from NIT Warangal. Currently working as assistant professor in NIT Warangal. He has an outstanding academics and professional background with a rich experience in communications and signal processing. He attended several conferences, published many papers and books. He also completed many funded projects. Thank you, sir, for being with us. Now, I would like to hand over the sessions to Dr. Puli Kishore Kumar, sir, to share his valuable insights with us. Welcome you, sir.
Yeah, very good evening. Thank you so much for that nice introduction, ma'am. I hope my screen is visible to you.
Yes, sir. Yes, sir.
And even the voice also.
Yes, yes.
Today, I would like to thank, first of all, the organizing team, specifically the head of the department, Professor Nageshwar Garu, for considering me as one of the expert speakers for this Atal FTP. Even the principal and head of the organizations and the Vadwell sir and all the faculty members who were part of this organizing this Atal FTP program. And for the audience, my sincere request is I would like to request you at any point of time, if you face difficulty in understanding, without hesitation, please at least drop your query in the chat box, or you can unmute yourself and you can ask the questions. This is one option that I'm giving to you. My agenda, I'll try to make for today, it will be something like this. I'll try to just define what actually the radar is and why UWB technology is required, that I'll tell you, and then machine learning algorithms, how it is going to be used, because the topic that was given to me is DOA estimation specifically for vehicle to X environment, vehicle to vehicle or vehicle to ground or vehicle to satellite or whatever it is, vehicle to UAV, which is one of the most demanding research area nowadays, because we are using most of us are aware of the drone technology, and we specifically for surveillance situation, we should be in a position to identify the location of the drone, in the sense the range as well as the angle of arrival, which is also considered as the direction of arrival. Okay, so most of the things that are available with us, we'll try to make it with you. We'll try to convince you based on the research work that was happening at NIT Andhra Pradesh. So again, I'm saying without any hesitation, if you face any difficulty in understanding, please unmute yourself and ask the query. Okay, yeah. So let us start with the radar. So radar, which is actually having the acronym of radio detection and ranging, radio in the sense we'll be using radio frequencies or electromagnetic signals, specifically in the radio frequency range, starting from some 20 hertz or 20 kilohertz 20 hertz to even millimeter wave, all these are considered, all electromagnetic signals are considered as radio signals. Actually, the term radio is wrongly used in our conventional what we know actually about the radio is actually the AM radio receiver or FM radio receiver. But to be more specific, radio is nothing but all electromagnetic energy receiver. It can be even TV is also considered as radio, walkie-talkie, which receives the electromagnetic radio signals, radio frequency signals. So initially the radar, the acronym when it coined this word, when the word is coined, it is considered for a detection and ranging. Detection means identifying the object, whether there is an object or not, we have to detect it, and then identifying the range of that particular target. Detection of the target and identifying the range of the target. But nowadays radar, it is going to have multiple applications. Even if you try to look into the radar guns which were being used especially in the highways to estimate the speed, velocity of the moving vehicles. Till if that can be considered as a starting point, local surveillance also we can use, and we can even go for the defense applications where the objective is to identify or to target, to find out the target direction, range, and even azimuthal location. And you know what? Nowadays, radar imaging is also another specific application where the surveillance is going to be taken place, where the normal visible light cannot do the task, where visible usually during the night times visible light is not in a position to give the image. So in that particular context, for surveillance, radar imaging is one of the most important thing, and ground penetrating radar, many applications are there as such. Okay, so initially when it was coined, the purpose is only for detection and ranging, but now the applications are many. So how it is going to detect the range? What we are going to do is we are going to transmit the pulse, and then we are going to have the received echo signal. You can see in this particular animation, we are going to have a transmitted pulse and received echo signal is getting spreaded. To be more specific, whatever the signal that we are transmitting also will be having the spreading factor. But the point over here is this is a directive antenna where the energy is being launched in a specific direction. That is the reason why it is being displayed over here as a packet traveling from the transmitting antenna to the target. If you try to look into this waveform, when it initiates from the source, and then again when it is being received by the same antenna, when it is being received by the antenna, we are going to get the pulse. So till then, there is no received echo signal. Usually, practically what happens is there will be a noise that is being received by the receiver, and multiple reflections will be there. Many things will come into picture. So there comes the radar signal processing, where when to take the decision, whether if the received signal threshold goes beyond the threshold limit, which is going to be fixed by different approaches. If it is going beyond that, then we can able to properly detect the target, and then if it is below that, we can consider it as a noise. There actually different terminologies comes into picture: probability of detection, probability of false alarm, probability of misdetection. All these things links with the threshold which you are going to set for detecting the target. So you may ask the question how this is going to link to the direction of arrival estimation, because direction of arrival estimation, if we try to identify the range, does it links with the direction of arrival estimation? That we'll try to see it little later. Radar does nothing but measures the round trip time delay. So it is going to measure the round trip time delay from the transmitting point to again receiving the echo signal. So once you identify the round trip time delay, then we can able to use the equation R is equal to C into T by 2, where T is actually the round trip time delay. Okay. If I assume that the transmitting signal power is PT, then PT divided by 4 pi R square is the spreading factor that we are going to have, and this is going to be multiplied with the gain of the transmitting antenna hits the radar target, which is going to have the radar cross section of sigma. Then again, this is actually A effective is nothing but effective antenna aperture area, which is in meter square. So this is actually going to affect the received signal power, and hence the total received signal power is going to be represented like this. So the gain, since G is equal to 4 pi A divided by lambda square, we will be having the received power, which is actually proportional to 1 by R to the power of 4. You will be getting very, very less amount of uh, received power, because the distance, sometimes it will be in kilometers, or sometimes it will be in even meters also. Why I'm saying in meters is specifically when in indoor surveillance. When it comes to the indoor surveillance, recently we tried to draft a proposal. The intention is we are going to use the indoor radar. Usually we'll go for ultra wideband only. Why ultra wideband? You'll come to know little very soon. So the purpose of that indoor radar is to monitor the patient, remotely monitor the patient, or remotely monitor the elderly people. So what we will try to do is we'll try to find out the signatures of the target object. It can be a patient, or it can be a old person. So usually what happens is the regular activities, we'll try to collect the signatures, radar signatures for the regular activities, and we'll keep it in the database. And unlike the regular activities, if there is anything uneven thing happened, for suppose suddenly falling onto the ground, or something like skid, some uneven activity, if it is sensed by the radar, that information first it has to sense that this activity is the unevenness that is happening, specifically related to the patient or elderly person. And then once it detects that it is an uneven activity, it should alarm the person who is going to be in the remote area. Maybe it can be a nurse, or it can be some other person who is in the nearby room. Or so see, this actually helps. Yeah. In United Kingdom, and I tried to contact with a person where we had a joint project proposal. Details I'll share it with you a little later. But yes, yeah, the range of the target can be in meters, it can be in kilometers. Meters for indoor surveillance, and kilometers specifically in outdoor environment, in a defense environment, where we are supposed to identify the range of the target, or angle of arrival estimation, angle of arrival or direction of arrival estimation of the target. Okay. So you can see over here, either pulse modulated or frequency modulated sinusoidal is used for transmission depending upon the application. So we all know what actually the modulation is in communication, specifically why modulation is required. If we start with the analog modulation techniques, AM, FM, many things are there. And digital modulation techniques, QPSK, QAM, 4CAM, 16QAM, many modulation techniques are available. So ultimate aim of choosing these modulation techniques, it has a different objectives in communication. But why modulation is required in a radars? Whatever the signal that we are transmitting to the towards the target, does the modulation or shape of the waveform affects the parameter estimation, whether it is range or angle, that we'll try to see now. So usually what will happen is the pulse modulated or frequency modulated sinusoid is used for transmission. And you can see over here, the signal is actually considered as a linear frequency modulated. Here the time period is a little larger as compared with the time period that we are going to have over here. So in the sense that the frequency is linearly increasing over here, the same is going to, this is actually considered as a linear frequency modulated waveform. On off switching we are going to do. Considered as the narrowband radars because their bandwidth is less than 10% of the central frequency. So here what actually is being considered is if it is unmodulated signal. Here, what I showed is actually the linear frequency modulated. If it is unmodulated signal, what happens is the radar is actually considered as a narrowband radar. How you are going to give the differences between narrowband, wideband, and ultra wideband? Fractional bandwidth is the parameter which is going to decide this thing. So the fractional bandwidth, if it is less than 0.01%, then usually it will be considered as the narrowband. Otherwise, it will be between 0.01 and 0.1, it will be considered as wideband, and above 0.1, it will be considered as ultra wideband. Okay, so you can see here one more waveform that is being used specifically in radars. This is a linear frequency modulated waveform. And in the sense that we are going to use some modulation techniques even for sensing. I'll make it clear why modulation is required. What will happen if modulation is not required? What are the effects that are going to happen if a modulation is not there? That I'll try to explain it to you a little shortly. And then we'll switch into the direction of arrival estimation by making use of the neural networks. And then, yeah, for vehicular to V2X environment, how this is going to be handled, that I'll give you the information. Okay. So yeah, this is a stepped frequency waveform. You can see in this particular time instant, we are going to have the frequency F1, F2, F3, F4, F5. You see, this is the frequency, and F1 is smaller than F2, F3, F4, F5, F6. So this type of waveforms also is required. Why it is required? We'll try to see. As per the FC definition, the fractional bandwidth should be greater than 0.2 for ultra wideband. You see here, we will be having narrow band and wide band will be in between these two. For ultra wideband, we need to have the total transmitted power should be less, very small. It should not interfere with the existing environment radio receivers, because when the bandwidth is very large, it is very prone to interfere with the existing radio receivers. To overcome that, yeah, there is a limit called minus 41.3 dBm per megahertz. You can see it over here, minus 41.3 dBm per megahertz, which is 74.1 nanowatts, which is actually the maximum allowable power limit for televisions and computer monitors. If you are going to have more than this, it is going to interfere with the existing environment, existing devices. So that's the reason why they kept the maximum transmitting range as per the FCC definition. As I told you, the fractional bandwidth is going to play a vital role. BF is equals to FH minus FL. This is the bandwidth, and FH plus FL by 2 is considered as the central frequency. Okay, either pulse modulator or frequency modulator sinusoidal is used for transmission. Unlike the narrowband 6, one thumb rule, what we can able to say is usually narrowband communication or narrowband radars, or whenever you say narrowband, usually the carrier that is being used is a sinusoidal signal. Unmodulated sinusoidal signal. That's the reason why we'll be calling it as amplitude modulation is considered narrowband. Many of the GSM, CDMA is considered as wideband. As such, we don't have the ultra wideband based devices as of now, but it is still in the. I think many products came outside. Those details as of now, I am not showing it to you. Okay, so narrowband has advantages and disadvantages. As they are narrowband, interchannel interference is not a big problem. So when you try to look into the very first radar, yeah, I just want to show something. Yeah, you can see over here. Initially, people try to use the spark gap transmitters. You see here. I just try to keep it somewhere. Yeah, you can see here. This is a Hertz experiment that demonstrates the electromagnetic energy transmission and receiving. You can see here there is an induction coil which produces very high voltage. This is the very first experiment that is done by the Hertz. That's the reason why we have many times we use it to call Hertzian dipole also, even antenna theory. So we are going to have induction coil which produces very high voltages, and here are two spheres, and we are going to have a very small gap between these two spheres. One is given the positive charge, and another one is given negative charge. See, the moment when we turn on the switch, what will happen is large amount of charge is getting accumulated over these two spheres, and that charge, here the charge density is very less, charge per unit area, because the area is more. But the moment when you come over here, charge per area is very small. So charge density is very high. So the moment when we turn on the switch, there is a chance for this very high voltage, the spark, the discharge is going to take place, which is actually the demonstration of the electromagnetic energy. transmission. And whatever the electromagnetic energy that is being transmitted from here, it will be received by this coil, which is again having a very small discs over here. You see here small spheres are there, and this will be collected. So this is the very first experiment that is being that was demonstrated at the time of Henry Hertz in the year 1887. Actually, I will try to look back into the Maxwell's equations. What I have shown to you, see, let us look into the genealogy. So, in 1861, Maxwell came up with the contribution of this dou by dou t. If dou by dou t is not there, which is considered as the time rate of change of the displacement flux density, uh, which is actually the circulating magnetic field is being caused by this current density and even changing electric flux density. Changing electric flux density. If it is stationary, then it will not have the circulating magnetic field. So the actual contribution of the Maxwell is this one. Contribution of Maxwell is dou by dou t. Ampere told that the current carrying conductor will produce a circulating magnetic field. So yeah, there are some situations where this Ampere's law fails, and that's the reason why. When the moment when I turn on the switch, you see here on the boundaries of the Amperean loop, we are going to see the change in magnetic field. But as such, there is no conduction current that is penetrating through the surface. So there comes the change in the electric field, flux density between these two parallel plate capacitor. So what I would like to say is that equation combined with this equation will try to produce the electromagnetic energy, and that's what is being demonstrated by the Henry Hertz in the year 1887. So 1887, he just demonstrated the electromagnetic radiation. And the initial experiment is impulse-based signal. Impulse-based signal means the initial communication is actually ultra-wideband. Ultra-wideband, very large bandwidths. So people try to use it for detecting the ships. Practically demonstrated in 1887, Heinrich Hertz, a German scientist, practically demonstrated the generation and detection of electromagnetic waves, proved Maxwell's proposal. Maxwell proposed this in 1861. 1861, yeah, in 1861. Ampere's law came long way before, that is 1826. Anyway, this is actually the history, but what I would like to say is, initial thing is of a spark gap transmitter which occupies the frequencies from 3 hertz to 300 gigahertz. We don't have any communication system in the present world which is having this much very huge bandwidth, 3 hertz to 300 gigahertz. Later work in radio engineering was almost entirely at longer wavelengths, less bandwidth. The reason is interchannel interference. So, as I told you, this is being used for detecting the shifts, but two similar sources, if I try to use, maybe at some a far distance apart, but what happens is for detecting two different targets. Again, I'm saying for detecting two different targets. In that case, the interference is going to happen. That's the reason why people shifted to the long wavelengths, where we can able to finally comfortably tune to a specific frequency, like 93.5 megahertz FM radio. Then, if I want, I can tune to 102.2 megahertz FM radio. So all these things are coming up because of this lowering the bandwidth. Specifically, what we are going to do is we are going to specifically fix the bandwidth and the channel frequency. Okay, so that's what is being happen. But as I told you, it will be in the initial days. It is at the beginning of the communication itself. It is UW, but now again people move to the UW because of the advantages that it is having. As I told you, narrowband, the thumb rule is it will have the unmodulated sensor signals, and ultra wideband, the thumb rule is it will be having non-sensor signals. So we'll be using non-sensor signals for this ultra wideband technology. Okay, let's come back to this modulation techniques. Why modulation is required in radar, specifically how it is going to affect the radar range and radar direction of arrival estimation. Okay, so yeah, you can see over here. There are two targets which are 100 meters apart. and we are sending a pulse which is of 1 microsecond duration, 1 microsecond duration. So 1 microsecond duration means C is equals to n lambda. C is equals to n lambda. So when I try to calculate the length of this particular where you will be getting 300 meters. 300 meters duration you are going to have. Okay, so what's happening in this particular animation is we are receiving the echoes from the two targets, and unfortunately, the echoes from these two targets are getting overlapped. And the receiver, it receives only one echo, and it will take the decision that yes, there is some target, only one target. It is saying it is not in a position to distinguish two targets which are very close to each other. So this is the problem what we are facing. So as I told you, why modulation is required. So this is the place where modulation plays a very vital role, because you see here, if I try to have on my, let me show you one more thing. Here it is 300 microsecond duration, but the distance between two targets is 200 meters. You can comfortably see that we are receiving the two different echoes, indicating that two different targets are there. So even to increase the range resolution, what we are supposed to do. So mathematically, if you try to see the distance between two targets, we would like to have as small as possible, which is depending upon C by 2b, C into tau by 2, where C into tau is actually the length of this pulse, C into tau. Okay, C by 2b means we are going to have the bandwidth dependency. If the bandwidth is more, C by 2b value will be very, very small. Okay, so that means two targets which are very close to each other, we can able to distinguish properly. So this yes, please.
Details இல்ல ஒரு பர்சனுடைய ஜெனடிக் டேட்டா இல்ல பயோமெட்ரிக் டேட்டா, இது எல்லாமே மெடிக்கல் டேட்டா ரொம்ப இம்பார்ட்டன்ட். இதை பிரீச் ஆகாம நாம பத்திரமா பார்த்துக்கணும். தென் ஃபினான்ஷியல் இன்ஃபர்மேஷன் இப்ப பாத்தீங்க அப்படின்னா இட் இன்க்ளூட்ஸ் இன்ஃபர்மேஷன் ரிகார்டிங் பிசினஸ் டிரான்சாக்ஷன், பேங்க் டீடைல்ஸ், இல்ல கிரெடிட் கார்டு நம்பர்ஸ், இல்ல அவங்களுடைய பேமெண்ட் ஹிஸ்டரி, இது எல்லாத்தையுமே நாம என்ன பண்ணணும் அப்படின்னா.
Yeah, you can proceed, sir.
Okay, thank you, sir. So bandwidth plays a vital role. So that's the reason why we need to have a large bandwidth for distinguishing to get the more details about the target, specifically for sensing situations. So yeah, that's the reason why we require the modulation. And modulation usually increases the bandwidth. Whatever the modulation that you take, usually increases the bandwidth. And when it comes to ultra wideband, we are going to use this Gaussian pulses. Okay, so that gives you more information related to the targets. Okay. Next. Coming to the angle resolution, we just have found the range resolution. Range resolution means distinguishing two targets which are very close to each other in the range direction. So delta R is defined as the minimum distance along the radar line of sight between two scatterers, which they can still be detected individually. So we used to have this, even our eye is also not in a position to resolve two targets which are very close to each other. And if we are looking at a far objects, if you are looking at a very far objects, you can see that the good saying is that the mountains looks like a very smooth. The reason is it is not, our eye is not in a position to distinguish them. The moment when we come closer, then only our eye can distinguish the details. So even our eye is also having some resolution parameter. Okay, so when it comes to the azimuthal resolution. Azimuthal resolution means angle resolution. Why angle resolution? Because we are going to estimate the angles. So this is the very first place where you will be finding about this angle resolution. So you see here, this is a simple dipole antenna, and we are going to have the electromagnetic energy launching by this dipole antenna. And optimal length, people consider it as lambda by 2. If mounted in the ground, particle length is reduced to lambda by 4 because the ground plane is considered as the perfect conductor, and we are using the imaging theory so that the same dipole concept can also be applied over there. Reflection of ground gives its virtual length of lambda by 2, and this is the radiation pattern what we are going to have. So this is a simple dipole antenna. See, in angle estimation, antenna plays a crucial role. DOA estimation, antenna plays a crucial role. Okay, so ultimate aim is from which direction we are going to receive the signal, specifically from the target. So that angle we would like to identify, we would like to calculate, and for that reason we are going to use this particular radar. Actually, there is a concept called integrated sensing and communication, where the same communication system is also be used for sensing the environment. Okay, that's actually a different story. But yes, even in ISAC, the communication system is used to estimate the angle of the target. Yeah, okay, so now elementary dipole, we are going to have the radiation band something like this. You can see it's like an apple-like structure. So front view, side view, top view, all the patterns were given to you. So in the elevation plane, we are going to have 8-like structure, and in the azimuthal plane, it is actually the omnidirectional circle you are going to get. Okay. So when why directional antennas are required, directional antennas will try to launch the energy in a specific direction, and it even receives the energy in a specific direction. That's the benefit of the directional antenna. Unlike the omnidirectional antenna, which we have seen earlier, this directional antenna is used for specifically linking to specifically connecting to a target which is in a desired direction. For suppose, if I want to have more coverage in all directions, specific example is cell tower. We use this monopole or dipole antennas. So all 360 degrees it should have the coverage. But when it comes to the DTH receiver, which we use the antenna which we use for receiving the television channels, we use the dish antenna, and that orientation of the dish antenna is towards a specific satellite. So it is going to receive the signal from that specific satellite. Okay. So when you know from which direction you are supposed to receive the signal, then you try to increase the gain of the antenna in that particular direction, which actually considers the directional antenna. This directional antenna, specifically the beam width of this directional antenna, plays a vital role in defining the angle of arrival estimation, resolution of DOA estimation. Okay, direction of arrival. In the sense, just like the way how we have considered two targets in the range direction, we will be considering two targets with a minimum angle variation. For example, let us consider one target at 10 degrees and another target as a 10.1 degree. You see the difference is only 0.1 degree. So whether the radar which you are using for sensing for the DO estimation, whether it is in a position to resolve these two targets separately, or whether it will say that yes, only one target is there at somewhere at 10 degrees. Because the nearest integer to 10 and 10.1 degrees is 10 only. So roughly it will say that at 10 degrees some target is there. Whether your radar is having a very good capability of resolving two targets in the angle direction, which will consider the angular resolution. Okay. So that actually depends upon this antenna. So what signal processing methods are used, and how neural networks are going to help us in a DOA estimation, that we'll try to see. But for DOA estimation, this antenna plays a crucial role. Okay, you see here we can able to define different parameters for this antenna, like first null beam width and half power beam width, main lobes, side lobes, minor lobes, many things we can able to define. Okay. So you can see here the gain. If I assume this circle is isotropic and now its radius power of this is in all the directions, unlike the isotropic antenna, unlike the omnidirectional antenna, you will be having more gain for these directional antennas. The energy will be traveled. The energy, the power of the signal that we are transmitting will be more in this particular direction, and the same thing is going to happen even in the receiving phase also. So ideal antenna is considered as an isotropic vertical dipole, omnidirectional radar dish or horn antenna, or a small dish also more or less will be under the directional dish. Yes, here comes the angular resolution. When you see the angular resolution, just like the way how we define the range resolution to distinguishing two targets which are very close to each other, specifically in the range, like in the sense, for suppose if I have a target which is at 10 meters and another target at 10.1 meters, whether my radar is in a position to resolve two targets separately or comfortably, it will says that one target is there at 10 meters. If it says like that, then your radar is not having a good range resolution. A similar definition we can apply even for this angular resolution. So in angular resolution, if we have two targets, one is at 10 degrees and another one is 10.1 degree, and if you are supposed to resolve these two things, then you need to have a good antenna with a very narrow beam width. So to have a narrow beam width, your aperture area should be large enough. Okay. So you can see over here, yes, this angular resolution is depending upon the range. So when you take a torchlight and when you try to put it on the wall, you'll be getting a small circle. And when you go far from to the wall, and again if you try to put the same torchlight onto the wall, then the circle will become bigger. So if circle is becoming big, means its beam width is more, and it is not in a position to resolve to targets which are in that particular circle, which is actually called antenna footprint. Antenna footprint. So the narrower the footprint area is, the more resolution capability one will have in resolving two angles separately. Okay, so you can see here SCA is greater than or equals to 2R into sine theta by 2. Your angular resolution is directly linked with the theta, which is nothing but the beam width, and it is also related to the R. So the distance between two targets in the angular direction, the SCA, it will increase if R increases. So that means for it is the same radar antenna. If you try to move away from the target, then it is difficult to get to targets. That means angular resolution, you will not get a good angular resolution. Okay. The best thing over here is to have a very narrow pencil beam like structure so that you can able to steer that beam in whichever the direction that we want to have a very good angular resolution. So yeah, here I already told you the information about probability of false alarms. Okay, UWB technology, I'll keep it aside. Let me move ahead. Yeah, this is one figure where you can able to distinguish the between narrow band, wide band, and ultra wide band. Wide band CDMA will comes under the example for this ultra wide band signals. Okay. Yeah, let me not do these things. Before going to the machine learning, I'll tell you how people used to do this DO estimation earlier, and then I'll like, give the glimpse of machine learning, and then we'll try to see how this DO estimation specifically for people to V2X environment, how it is going to be. So here two dipole antennas are there, arrangement of antenna elements in the linear pattern. So actually the length of the dipole is lambda by 2 and the distance between two antennas is lambda by 2. You can see here from from this vertical line, the antenna is lambda by 4, and from here to here, antenna is lambda by 4. The distance between two antennas is lambda by 2. Okay. So now what I want to say is, if you try to have two antennas, for single dipole antenna, we are going to have the radiation pattern, which is the omnidirectional radiation pattern, apple-like structure in three-dimensional plot. So if I try to keep two antennas near to each other, how the radiation pattern will be? So at a point in the free space, which is in the far field region, we are going to, if we assume these two antennas as the transmitting antennas, at a point P in free space, which is very far from these two antenna elements, the electric field intensity will be the sum of the electric field intensity of these two antennas. So in the sense, the electric field intensity due to the first antenna at the point P, electric field intensity at because of the second antenna at the same point. So if you try to add up these electric field intensities and then and then if you try to simplify the expressions, actually you will be getting two terms. Let me do that thing from here. Let me do the sharing once again. Stop share. Yeah, I would like to show this slide now. One second, I'll share you one more presentation. Yeah, one second, please. Yeah, I hope you can see this.
Yes, sir.
Okay, so in DO estimation, what we are going to do is we are going to have two antenna elements. Specifically, as I told you, for angular resolution, the beam width of the antenna plays a vital role. So for that reason, I'll just show you a case over here. Instead of having two antenna elements, if I try to have multiple antenna elements, I'll show you the mathematical model. Okay, so you see here, antenna element 1, 2, 3, 4, 5, and so on up to n antenna elements are there. So the signal that we are transmitting, we will be having some magnitude and the phase parameter. So S1 into e power j omega t is the signal. S into e power j omega t is the signal. So what happens is, so when I try to have this antenna arrays, so the signal from the far field, if you try to see over here, there is a target over here. Let us assume that this target is in a very far field region, and the received signal from this particular target, we are going to have parallel lines drawn over here. In the sense, there will be a line that is drawn something like this. Let me take this. So you will be having a parallel line something like this. You'll be having one more parallel line something like this. One more parallel line something like this. So if you carefully observe, there is a path difference that is happening. There is a path difference that is happening. So that path difference is going to be represented with this delay element, that is e power j omega t minus k1 into d. So this k1 into d, if I assume that the distance between two elements is d distance apart, then d, if I try to consider this as a theta, if this is theta, you just check it out over here. You will be having 90 degrees angle over here. So we can able to model this as a d sine theta, 2 pi by lambda into d sine theta. Okay, so this is actually the pattern of the received signals that you are going to have, in the sense that the received signal, this, if I assume that there is no extra path for the received signal over here, then you will be having this phase parameter 0, and hence e power 0 will be going 1. Okay, the second element will be having e power j 2 pi by lambda into d sine theta. This is actually the extra phase that you are going. So each and every AND element will contribute some phase, and this phase will be having some pattern. In the sense, first one will be having the extra phase of 0 phase, e power 0 is 1. Second one is some 5 phase. This, if I assume that 2 pi by lambda into d sine theta has some 5, e power j5 extra phase, you are going to have e power j25, e power j35, e power j45. It depends on the different antennas that the number. It depends on the number of antennas that you are going to have. Okay, so now coming back to this presentation. Yeah. Coming back to this presentation. So we are going to have the radiation pattern. We are going to have the radiation pattern of this antenna element. Let me erase this. Okay. So the radiation pattern of this individual element multiplied with the array factor will gives you the overall radiation pattern. Okay. As such, the derivation is not included here. But what I would like to say is, if I try to have more number of antennas, and if you try to feed each and every antenna with the different phases, the first antenna with 0 degrees, second antenna with the delta phi, 2 into delta phi, 3 into delta phi, 4 into delta phi, 5 into delta phi, because there will be the path difference that as I explained to you in the earlier case. So you can able to steer the beam. You can able to steer the beam in whichever the direction that you can able to have by controlling the input phase of the antenna. Okay, specifically the array antenna. So by controlling the phase, you are going to have the steering of the beam. The same is going to happen even in the received signal. So you will be receiving the signals from different directions, and that received signals, what we'll do is we'll try to receive it, and we'll try to we'll try to estimate the phase at each and every antenna element, and based on the phase values that you are going to get, we will be in a position to assess from which direction the target is coming. Okay, so electronic beam steering is done by changing the phase of the input of the antenna. Okay, so phase array antennas, each antenna element can be controlled individually. By changing the feeding, it is possible to construct a direct beam. Okay, so now this phased array can be used both for transmission and receiving. If we use for whatever be the case it is, that means whether transmission or receiving, the beam width will be very, very narrow. Narrow beam width you can able to achieve by using of this antenna array. Okay, can't we? So if at all I want to have the same beam width with the physical, you may require to have very high, a large dimension of the antenna, a large size of the antenna. But if you use the antenna arrays, you can comfortably keep the antenna array length whichever the way that you want, so that you will be getting the very narrow beam width. Okay, so that's about that here. So xk of t is equals to e power minus omega tau k into x1 of t. X1 of t is a signal that is being transmitted. Okay, and yeah, it is clearly mentioned here. If S of t is the target, then this path I'm going to consider it as a reference path, and you see this is considered as a d sine theta. How we are going to get this? This is a d, so this is 90 degrees angle. So this is 90 degrees angle. If this is a theta, you will be having this is also theta. So if this is theta, then you are going to have this will becomes 90 minus theta. 90 minus theta means if I try to have this, if I try to complete this triangle, if I try to complete this will becomes d, and this will becomes this will becomes theta. So you'll be getting d sine theta is in this particular direction. If this is d sine theta, the vertical will becomes the d cos theta. So this is the extra path that is going to give you the extra phase value. That extra phase value is going to be used for the angle detection. Okay. Okay. Uniform linear array received signal will be something like this: xk of t e power minus j omega t into x1 of t. So here for k you will be getting k minus 1 into d sine theta by v. Okay, 2 pi by lambda into d sine theta. That is what we are going to 2 pi by lambda into d sine theta. This is the phase parameter. And the overall signal, when I try to perform the summation, xk of t means k is equals to 1, the signal received at the first antenna element. Signal received at the first antenna element, you can check it out over here. E power minus j into k minus 1. 1 minus 1 is 0. No phase at all. No extra phase is being added over here. K is equals to 2. 2 minus 1, 1 phi is going to be added. 2 phi is going to be added. Okay. So yeah, mathematically we can write this as x1 of t is equal, in matrix notation is this one. This is actually considered as the array factor. So this array factor pattern decides your radiation pattern. Okay. Linear equation, matrix linear equation, x of t is equal to a into s of t plus n of t. Yeah, uniform linear array radiation pattern. The total antenna response is generally the multiplication of the single element response and the array factor of the array. The array factor of the uniform linear array consists of n elements. So this is the array factor of the uniform linear array, which one can able to comfortably derive this equation. So if you try to plot the array factor, it will be something like this. And if I try to do the multiplication, this is a single dipole radiation pattern multiplied with the field pattern. This is for the field pattern array factor of 4 isotropic sources, 4 dipoles. So this is the overall radiation pattern. If I try to increase the number of antenna elements, obviously this main lobe will become even narrower and narrower and narrower. Okay. So, and you see, this is actually the antenna elements. 1, 2, 3, 4, 4 antenna elements. So at the center, you are going to have this radiation pattern. Okay. So more antenna elements, I mean, the beam width will be very narrow, and hence you can able to resolve two targets. When it comes to the DOA estimation, angle of detection of the target is very important, and resolving them is also very important. So you can do the arrangement of antenna elements, whatever the pattern that you want. You can try it: rectangular array, planar array, maybe L-shaped array, T-shaped array, X-shaped array. So each and every array will be having its own advantages and disadvantages. So yeah, this is the uniform rectangular array factor. So you can see here the array factor for this one is something like single-leg structure. The same single-leg structure you are going to get, but this is in three-dimensional plot. Okay, array factor matrix in X direction, array factor matrix in Y direction. Okay. L-shaped array, the array factor matrix will be something like this. So what I try to do is I'm just showing you the array factor pattern. So this array factor pattern, we have to multiply with the dipole radiation pattern so that you'll be getting the overall radiation pattern. Okay. Now, this is for L-shaped, T-shaped, F-shaped array, plus shaped array. And as I told you, if you multiply with the overall radiation pattern, then we'll try to get the array radiation pattern. DOA estimation algorithms for 1D uniform linear array. Here comes the direction of arrival estimation. Okay. So, you know what? The received signal at each and every antenna element is actually assumed as the random variable. Probability concepts we are going to use for DOA estimation. Okay, for suppose if I try to have 5 antenna elements, so the received signal is very random in nature. It is an IC signal. Okay, so it is something like a 5 random variables. 5 antenna elements means 5 random variables. So different methods are available. Different methods are available. Specifically, correlation-based DOA estimation. See, whatever the concept that we study in signals and systems, we'll be using over here. In correlation-based DOA estimation, what we'll try to do is, since we know what is the signal that we are transmitting, we will try to calculate the correlation between the received signal and the transmitted signal. So I'll try to show you the idea. Okay, so you see here, this equation is very familiar to us as of now. X is equals to AS plus N, where S is the signal, A is the array factor, and X is actually the received vector. X1, X2, X3, X4, and so on, Xn we are going to have. You try to see this array factor matrix once. Okay, so A of theta 1, A of theta 2, A of theta 3, A of theta 1 is nothing but 5, theta 2 is nothing but 2, 5, 3, 5, 4, 5, 5, 5, and so on, and 5. So now what we are going to do is, this array factor matrix we will try to generate for all angles. Because for a specific angle, let us assume for phi is equals to 10 degrees. Phi is equals to 10 degrees. A of theta 1 usually will be 1. A of theta 2 will be e power j 10 degrees. A of theta 3 will be e power j into 2 into 10 degrees. So for each and every angle, we will try to calculate the array factor. Okay. Then at the receiver, what we will try to do is, we will try to correlate it. So if X is equal to S plus N is the received signal, the easiest way to estimate the angles is through correlation. The correlation method plots P of theta versus theta. What we are going to do is, we are going to do this spectrum, spatial spectrum. P of theta is considered as spatial spectrum. Here, theta is going to vary from minus 180 to plus 180 or minus 90 to plus 90. You can check it out. So for all values of it, just like the way how you are going to plot the frequency spectrum at different frequencies, how much amplitude you are going to have, how you are going to plot this frequency spectrum. Just like the way how we do this thing, we will plot the spatial spectrum. Spatial spectrum objective is at a different angles, how much amplitude you are going to get. At theta is equals to 0, how much amplitude you are going to get. At theta is equals to minus 90 to up to plus 90. For each and every angle, how much amplitude you are going to get. We all know one thing. For suppose, let us assume that the frequency f is equals to some 20 hertz. I am going to get the peak. Then I can comfortably say that the signal is consisting of 20 hertz frequency. Assuming that all other frequencies are having less than threshold or even very small amplitudes. So a similar concept we'll be using. So if I try to plot the spatial spectrum specifically in terms of the theta from minus 90 to plus 90, I'll try to plot its spectrum. How we are going to plot this thing, I'll tell you. We are using the tool correlation. So minus 90 to plus 90, we will try to plot the spectrum, how it is correlated to the received signal. So received signal will be having specific angle, if I'm not wrong, because if you are going to have a target at a specific theta 1 value, then it is that the received variables, whatever we are going to have, received signals, received signal will be having some correlation with the transmitted signal. And this transmitted signal specifically, we will be generating it generating the array factor matrix for all the possible angles within the range of surveillance. If your range of surveillance, that range of scan, if you assume it as minus 90 to plus 90, so we have to generate the antenna array factor for minus 90 to plus 90, and we will try to perform the correlation of this with the received signal, and to whichever the angle, that means you see here X is the received signal at all antenna elements. A Hermitian is actually the antenna array factor. You see here, if I assume 1 by n, then this will becomes A matrix will becomes 1 by n vector, and this is also you'll be having 1 by n vector. So if I try to perform this product, you'll be getting a 1 by n vector. This will becomes n by 1 and 1 by n. So you'll be getting P of theta for that particular theta. Here AH, you are going to have AH value for different angles. So see, as I told you, 1 by n for the angles ranging from minus 90 to plus 90, which is actually our search area of direction of arrival estimation. So for this search area of minus 90 to plus 90, we will, if we assume that the angle of increment is 1 degree, so minus 90, minus 89, minus 87, minus 86, 1 degree increment, then you are going to have 181 angles. So what we'll try to do is we'll try to have this A, which is actually the array factor matrix, which is if I assume 10 antenna elements, 10 by 181. So for each and every angle, angle, we are going to have 10 received signals. Okay. So this antenna array factor matrix 10 by 181 we will take, and the received signal is of dimension 10 by 1, 10 by 1 or 1 by 10. Okay. So if I try to perform this product A Hermitian times X, what I am expecting is a sample vector of 1 by 181. By 181 minus 92 plus 90 including 0 with 1 degree increment, you will be getting 181 angle. So ultimately P of theta we will be getting as 1 by 181 vector. 1 by 181 vector, the first element is corresponding to minus 90 and the last element is corresponding to plus 90, and this exact center value will be corresponding to the 0 degrees. That's what actually the spatial spectrum is. So we will vary theta from minus 90 to plus 90 degrees in the Hermitian of the array factor matrix, such that A Hermitian of theta into A of theta 1 will becomes maximum theta is equals to theta 1. You see here, instead of X, we are considering another array factor matrix that is specifically theta 1. And this A of theta 1, this product will becomes maximum only at A of theta 1, because it is having high correlation to A of theta 1 rather than with all other angles. So this is actually a correlation. Yeah, this correlation is also used for matching two signals for specifically for range estimation, but for angle estimation also we are going to have this correlation. But how good this is, it is not at all good. You see here, as I told you, minus 90 to plus 90, if I try to calculate the correlation algorithm for n is equals to 3, m is equals to 1, and SNR is equals to 0 dB. N is nothing but the number of antenna elements. Okay, n is nothing but the single target case. M is nothing but the target. So that target I assumed at a 10 degrees angle. Simulation for correlation with DO estimate. So at 10 degrees, it is going to exactly give the peak value. Okay, so yeah, it is going to calculate the correlation with the 10, because I assume the target at 10 degrees. So at 10 degrees, I'm getting maximum value. So the moment when I start deviating to the other angles, suppose 9 degrees or 8 degrees, 11 degrees, 12 degrees, the correlation will comes down. And that's the reason why you are going to have the plot something like this. But the correlation based DO estimation is very poor, angular resolution it is having. Okay, so yeah, this is the foundation. Then comes the music algorithm. Yeah, correlation algorithm for n is equals to 3 and m is equals to 1, SNR 30 dB. So we increased the SNR. N is equals to 8 and m is equals to 2 targets are there, 2 peaks you are going to sense, and SNR is equals to 30 dB. So conclusion is, we know that accuracy depends on unbiasedness. The increase of SNR, okay, but here the increase of number of elements is more effective than signal to noise ratio. So yeah, the angular resolution for this correlation based DO estimation is very, very less. Okay, maximum likelihood estimator. Actually, this maximum likelihood estimator is going to find out the probability, the received signal, whatever we are going to. So if I assume that the received signal as the fx of x, what is the probability of that received sample values? What is the probability that they are corresponding to theta? You just try to find out this probability. So in the sense that again, let us assume the 10 elements case, 10 and 9 elements case. So 10 and elements case, I receive the 1 by 10 vector. Okay. So I'll try to find out the probability of that received vector, or the probability of the. Remember one thing: the received vector, actually it is considered as the vector of random variables. So we'll try to find out fx of x given theta. So what is the probability that the received vector is of corresponding to theta, which is equal to 10 degrees. So you try to plot that likelihoodness. Okay, 10 degrees, 20 degrees, 30 degrees, 40 degrees. So when you try to see in the probability graph, whichever is going to have the high probability, that will be considered as the angle of error estimation. That's it. This is based on the maximum likelihood estimation. Okay, you can see here the maximum likelihood estimation algorithm for n is equals to 30 and elements and a single target case with 10 dB. You can able to recognize the target. Okay, so what we are going to do is we are going to calculate the likelihoodness of the each and every angle with respect to the received signal. Yeah, in music algorithm, what we'll try to do is we'll try to calculate the covariance matrix. Covariance matrix means what? We'll try to see how the see, when you try to calculate the variance gives the power of the random variable, expectation of x minus mu whole square. Whereas covariance, what it will says to do is how the other variable is getting affected. That means the expectation of x minus mu whole square. Instead of x minus mu whole square, we will try to write x minus mu x into x minus mu y minus mu y. X minus mu x into y minus mu y. So how these two random variables are linked, that we will try to calculate. After calculating the covariance matrix, you see here. S is equals to expectation of S into S Hermitian is the M by M matrix, which is actual covariance matrix. We will try to calculate the pseudo spectrum by making use of this equation, where RS is the N by N matrix with rank M. Therefore, N minus M. We will try to calculate the eigenvalues of the covariance matrix. eigenvalues of the covariance matrix we will try to calculate, and based on the eigenvalues, actually, in this music algorithm we should know how many number of targets are there, because so many eigenvalues we can able to get. Okay, so n minus m eigenvectors will be there and eigenvalues will be there. So if I try to have these two eigenvalues, then the angle corresponding to the eigenvalues will try to calculate it, and those values will be considered as the angle of arrival, angles of arrival. So you see here, this is a simulation. Music algorithm, correlation, maximum likelihood, these are the very fundamental. So very soon we will switch into the neural networks based, and we'll apply even the movement of the environment channel. If it is varying rapidly, how it is going to impact the neural networks, that also I'll show it to you. Okay, so you can see the results over here. Music algorithm performance. The one thing what we can able to conclude is, we try to conclude that as we increase the number of antenna, means number of snapshot. Number of snapshot means instead of taking with the single snapshot, let me say something over the snapshots. So if 10 elements are there, we discussed that we will be getting the 10 samples, 1 by 10 vector. So instead of taking 1 by 10 vector, if I try to consider 1 by 10 is 10 is the total number of antenna elements, and 1 is the number of samples that we are going to have. We usually will got a single snapshot case. Or suppose if I take 20 snapshots case, then the receiving signal will be 20 by 40. In the sense, for each and every 20 by 10, at each and every element we are going to have 20 samples. So 20 snapshots you are going to take. So yeah, the more the number of snapshots, the more the accuracy that you will be getting. But time consumption is also one of the key parameters that we need to consider. Compressive sensing based DOI estimation. Yeah, let me not deal this thing, but let me move on to the implement neural network based DOI estimation. Yeah, DOI estimation using deep learning. See, again, I'm saying DOI estimation basic objective is to identify the angle from which the target is coming. If your search space is from minus 60 degrees to plus 60 degrees, let us assume, then minus 60 to plus 60 means you will be getting minus 60 to 0, you'll be getting 60 degrees angle. So total 121 angles we will be having if you try to consider a 1 degrees increment. Minus 60, minus 59, minus 58, like that up to 0, and then 1, 2, 3, 4, 5, 6, and so on up to 60. So minus 121 angles you are going to have. So within these 121 angles, from which direction your target is coming, that is what the direction of arrival estimation means. So the search space plays a crucial role. So now if you try to increase the search space, no, my search space now it is not minus 62 plus 60. I would like to make it as minus 82 plus 80. Okay. Now you can define your own search space, and you can even try to have your own increments, because resolving two targets is one of the very important tasks that we are supposed to do. So as I told you, for suppose if I have one target at a 30 degrees and other target as 30.5 degrees. So whether your algorithm is resolving these two angles properly or not, that's what we have to check. Whether your radar is going to have good angular resolution or not, that's what we are going to see. Specifically in ISAC, which comes under vehicular to V2X communication, what happens is the existing communication system is being used for sensing also. So when the existing communication system is being used for sensing, specifically what will happen is the signals that are being transmitted. See, the base station will actually works as a sensing device. It will transmit the signals to the user. It will tries to communicate with the user, and in addition to the communication, what it tries to do is it will tries to get the reflected echo signal from the user to the base station. So this base station, now what it will tries to do is it will tries to assess at which distance my user is, at what distance my user is, and whether he is moving or not, it will tries to estimate. So with what velocity the user is going to do. So we are going to put the intelligence in the cell tower itself. That's what the V2X environment. V2X environment usually in the ISAC, we are making the cell tower intelligent enough to track the user such that much of the energy will be transmitted only in this particular direction. So I'll give you one application for this ISCSC where DO estimation is very, very important. For suppose if you try to consider the satellite communication link, so satellite would always tries to communicate into the base station. Oh, maybe it can be a DH receiver also. So what happens is if you try to incorporate the intelligence, ISCSC, integrated sensing and communication, yes, it is doing the communication, but in addition to the communication, if we try to establish the sensing capability to the same satellite, what will happen? It will try to sense the nearby targets. What targets will be there in the space? Yeah, debris, big stones, or whatever that moves in the space. All the things it will try to sense, and whether if that particular satellite is approaching to a target in the same track, then it should have the capability to identify to change its path so that it can be survived. The satellite can be survived. So that's what the intelligence of the integrated sensing and communication, which is going to happen in V2X environment. It is going to sense the target, it is going to estimate the angle of the target, range of the target, each and everything is going to happen. Okay, anyway, let's come back to the deep learning based DO estimation. Here, what we'll try to do is we'll try to again first fix the search space. So if I fix the search space as -190, then what we will try to do is, as I told you, with 1 degree increment, we are going to have 181 angles. So now the problem will simply considered as a classification problem, because we have some data and we just want to classify whether the data is corresponding to -90 or -89 or -87 up to +90. Yeah, is in between you will be having 10, 20, 30 degrees also. So we are going to find out the we are just considering the DO estimation the classification problem. The problem of DO estimation can be framed as a classification problem or regression problem. So for single source in classification problem where each angle is considered as a separate class, so we are going to have 181 classes. If I assume from -90 to +90 with 1 degree increment, we are going to have 181 classes. In regression problem where a single output target can be any of each angle. So what we are going to do in regression is we are going to estimate and we are going to perform the interpolation. We are going to perform the interpolation where a single output target can be any of each angle. So for multiple sources, the angle of multiple sources, angles of multiple sources, there is multiple DO estimations. By framing DO estimation, multiple sources or multi-level classification. So multi-class, multi-level classification. This is something like saying I have a few fruits and I just want you to classify the fruit as apple if it is red in color and some shape is there. Classify it into the class mango if the size of the fruit is something like this and color is something like this. So this is actually the classification problem, and we are going to fine tune this DO estimation as a classification problem. Okay. In deep learning, the problem of DO estimation can be formulated as classification. X is equals to 10, number of antenna elements 10, D is equals to 1 source, only one target, the number of features that you are going to have. So one important thing that we have to look into this DO estimation is a deep neural network is what data you are feeding to the input of your neural network. So that data plays a crucial role, vital role. Okay. So what we have done is we try to use this received signal, 10 antenna, since here 10 antenna elements are there. So each and every antenna element will receive some, assuming the single snapshot, one complex number will be available at each and every antenna element. So which is having both real part and imaginary part. So total we are going to have 20 such numbers. One is a real part and one is the imaginary part. The number of targets or labels is equals to 21. So what we are going to do is we are going to do the classification with the number of classes. 21 classes we are going to have, 21 labels we are going to have. So -10 to +10. The subspace is now from -10 to +10 degrees. the surface space is from minus 10 degrees to plus 10 degrees. So within this such space, we have to do the classification for the input data. So whether it comes to the class of minus 10 degrees, minus 9 degrees, minus 8 degrees, or 0 degrees, 1, 2, 3, 4, and so on up to 10 degrees. So that we are going to do it. That here we consider each angle as a class. The categorical cross entropy is used as a loss function. Atom optimizer is used, activation function, softmax activation function. So now in the very basic problem, we assume 3 hidden layers, and the neurons you can see here: hidden layer 150 neurons, hidden layer 250, hidden layer 350 neurons, and output should be of 21 classes. So after third layer, we need to have output 21 classes. Okay, so learning rate 180, 1 e power minus 5, and 100 epochs we have considered. So for 21 classes, 10,000 samples are used, for of which 80% are used for training and 20% is used for testing. The validation set is taken as 10% of the training set. So what we try to do is we try to generate 10,000 samples, 10,000 snapshots you can consider. 10,000 samples. See, what we have to do is for each and every angle we need to generate the data. For 21 were there, right? 21 classes are there. So I'll try to generate the data for angle 10. Maybe let us assume some 10 at different noise and environments. We need to train the neural network first. Actually, this is considered the multi-layer perceptron case. So we need to train the neural network. So first I'll try to generate the data for 10 degrees angle. Like 10 times I'll generate, and I'll train the neural network saying that this is 10 angle, class 10. Class 10 means positive angle 10 degrees. So next I will try to generate the data for 9 degrees, and again I will feed to the same neural network, and then I will say that this is class 9, this is plus 9 degrees. So likewise for all angles, I will try to generate the data and I will train the neural network. And I am defining this DO estimation problem as a classification problem. DO estimation problem as a classification problem. Okay, so total 10,000 samples were taken, and 80% are used for training, and in this 80%, 10% is used for validation. Validation means whether it is trained properly or not. So seen data, unseen data. Unseen data is for testing. Already seen data, we'll try to give as input, and we'll try to check it out whether it is giving the proper output or not. That's what the validation means. Okay, so we have know that if the validation loss increasing while our training loss is decreasing, then it means that there is a problem of overfitting. Okay, so yeah, you can see over here, this is the blue color line is the training, and orange color line is the validation that is happening. Deep learning model is used to classify 25 angles. The performance metrics of the deep learning model are training loss, training accuracy, validation loss, accuracy. So we can stop at 60. So you can see after 60, there is a possibility of having more number of deviations. So because of more deviations, overfitting may happen, and hence more error is possible. So that is the reason why it is advised to stop at 60. We can further improve the model accuracy by changing the hyperparameters such as the number of training samples, batch size, epoch of something. So this is a training testing loss, and this is the testing accuracy. We concluded from the above graph that the testing accuracy and loss is pretty similar to validation. Pretty similar to validation. Okay, so as a regression problem in deep learning, the problem of DO estimation can be formulated as a regression problem. Again, the same thing has been considered here. The target is a variable. The mean square error is used as a loss function. So again, you can see here 3 hidden layers epochs we have taken, and training. You can see over here at each and every angle we are going to get the peak value. Training loss and regression y same scale. If the batch size is equals to 1, the gradient descent algorithm is known as stochastic gradient descent algorithm. Stochastic gradient descent. The graph doesn't seem to be smooth because in the weight of the tool WT. So what we are going to do is we are just estimating. That's it. Okay. So now we change the architecture of the neural network. What problem we have faced is it is not working under low SNR conditions. The one which I have shown to you, it is not working at low SNR conditions. So we completely change the architecture of the artificial neural network. So we try to use, so far the results what I have, 21 classes are there, minus 10 to plus 10 degrees, hidden layer 1, 10, hidden layer 2, 20, 20, we have done this thing. With CNN, so CNN, what is the input that you are feeding? So usually what will happen in vehicular to X communication is the channel is going to vary rapidly. The channel is going to vary rapidly. So because of this, the received signal is getting affected more. The received signal. So the best way of estimating this thing is to assume the channel in the delayed Doppler domain. If we try to assume the channel in delayed Doppler domain, and if we try to get the received signal and feed it to this neural network architecture, then the chances of detecting this DO estimation at a very high, very low, very high noisy environment, it will be very good, specifically by making use of the neural networks. Okay. Yeah, this is the second architecture that was given, and for ANN you can see the training accuracy and training loss. Here the number of neurons has been changed. You see here two hidden layers, 10 neurons each, but here this is different. In this particular case, we are going to consider three hidden layers. First hidden layer 50, 100, 50. This is just the starting stage of using this DO estimation for neural networks for DO estimation. We try to do so many experiments in detecting the same DO estimation. Okay, we compared it with CNN also. You can check it out. The deep learning architecture CNN is trained to 21 angles. So what we have tried to do over here in CNN is we try to feed this CNN with the real part, imaginary part, and the magnitude part. So see, we are going to get the image like structure that we will try to feed to this input of the convolutional neural network 18/3. Okay. Okay. The noise plays a crucial role, specifically in V2X communication. So for that reason, what we try to do is we try to use the denoising autoencoder. We define a separate architecture for this denoising autoencoder to ensure that this particular architecture will work at a very low SNR. See, whatever the research that we have done, I'll show you the publications also. Our objective is to have a very good resolution. And then in addition to the good resolution, accurate estimation of the target. And to be more specific, at very high noisy conditions. Okay. So if the noise is very, very large, how you are going to make it? That's the biggest thing that you are going to have. Okay. So you see here sensor location. For that matter, you see we use it even the sparse arrays also. Sparse arrays means instead of using this uniform linear array or rectangular array or flash-shaped, L-shaped arrays, the sparse array concept, what actually it will try to do, it will try to help you to reconstruct or to achieve the same angular resolution with lesser number of antenna elements. So this concept is a little linked to your non-uniform sampling. So here what we are going to do is we are just performing the spatial sampling. In time domain, we are doing the time domain sampling, but this is spatial sampling. In DO estimation, whatever the received signal that we are having, it is actually considered as a spatial sampled version of the received signal. So if I try to use the sparse arrays and achieve the same angular resolution, then even if any of the antenna element fails, you can be in a position to achieve the good angular estimation, direction of angular estimation. So that's the reason why we use the denoising autoencoder. Spatial smoothing we have done, and then we straight away perform the direction of angular estimation. So these are the parameters what we have considered, and for different angles of how much mean square error we have obtained for different SNRs, you can see here. As the SNR increases, the root mean square error for T is equals to 1000, 10,000, 1,000, 100, 15, 25. It has been observed here. This is actually probability of detection. Probability of detection is very, very high as we increase the T value. So existing architectures, we try to do the fusion, specific architecture and maximum likelihood estimation. Why we try to do this maximum likelihood estimation in neural networks? The objective function, what actually is the thing that you are going to achieve? That's uh, the objective loss function is very, very important. So we have done this use for the same architecture for different objective functions. Same architecture but different objective functions. So whenever you are going to use the optimizer in the neural networks for training, what actually is going to happen is you are going to make use of that objective function, optimize that objective function. Okay. So if you assume that objective function has maximum likelihood estimation spectrum, likelihood function, then we have performed the results. Training accuracy 60%, training loss 1.53, and you can even see the results that we are going to obtain over here. So model accuracy for ResNet model. You see here it is somewhere around, training is the orange line and testing is of training is actually blue line and testing is of orange color line. So you can see that as we increase the number of epochs, because the number of epochs as such was mentioned over here is only 40. But if I try to increase the number of epochs, there is a possibility for you to have a very good accuracy. So now the thing over here is SCR target localization low SNRs using deep neural networks. Yeah, at a low SNR, very low SNR. Okay, so as I told you, one of the objective is to identify the angle or to estimate the angle at very low SNRs. Okay, right? So yeah, you can see over here many applications are there. Yeah, this is the proposed CNN model. One of my research scholars has proposed this CNN model where we are going to have n elements, n by n vector we are going to have with the three. What were these three? Real part, imaginary part, and then the magnitude. Okay, so each convolution layer consists of 64 filters. So that's this much big architecture is required for DO estimation. The answer to this question is the challenge that we have taken. So what is the challenge? At low SNRs. This is the actual challenge that we have taken. Very low SNRs. Okay. So I'll show you up to what level we have achieved this thing. Okay. You can see the architecture. Training accuracy, number of epochs. Yeah, you can see here at minus 15 dB. So you see 0 dB means the signal power is same as that of the noise power. 0 dB means because signal power is same as noise power, so you'll be getting the ratio 1, and hence you'll be getting log 1 as log 1 is equals to 0. That's what the 0 dB means. For suppose if the signal power is or if the noise power is 10 times 10 times of that of the signal power, that means S by N will become 1 by 10. So you'll be getting minus 10 dB. So if I assume that the signal power is 1 watt, the noise power will become 10 watts. So in that environment, minus 5 dB means it is a half, maybe it will be in between. Instead of 1 by 10 times of the signal power, maybe you'll be finding a value which is in between the same value of that of the signal power and 10 times that of the signal power. Okay. So in that particular case, at minus 5 dB, you see for CNNs per target at minus 5 dB. So you can see two targets we have considered. Here it is a single target case, here it's a two target case, and three targets case. Okay, so if let me show you one more figure. Yeah, index versus range. So for each and every value, we try to identify the same exact measurement of the target. So if the range is 7.5, 10, 10, 12.5, 20, 20. So for each and every value, the exact target estimation is going to be done. CNS for three targets from 1 meter distance. So here what we are doing is we are going to do the range estimation. range estimation. We even done the same thing with angle estimation also. So what is mentioned over here is the range. CNRS for 3 targets from 1 meters result at minus 20 dB, minus 20 dB noise. So mean square versus SNR plot. So deep learning techniques, if we try to use, the one benefit what we are going to have is to have a more accurate detection. See, there is a drawback even for this deep learning also. Because we need to first train that data, and if your model, if your environment is getting changed, in the sense specifically for V2X communication, if your environment is getting changed, then whatever the model that we have trained, that may not give the accurate DO estimation. But in that context, what we need to do is, during the training itself, whatever the parameters that it describes the changing in the environment, we have to consider it and we simulate the data, and we should train the neural network in that particular context. So we haven't worked for V2X communication for this DO estimation, but the conventional way, where the channel variation is not much. Channel variation is not much. In that particular case, we have done this DO estimation and we have achieved up to minus 20 dB. Minus 20 dB, there is no error at all. Okay. So yeah, that's from my side. And before concluding, I'll try to show you what actually the work that we are doing. We are having a couple of radar equipments at our campus. One is image beacon IR radar, where we are you can able to see the transmitting antenna elements over here and receiving antenna elements over here. This is also again a millimeter, 3D millimeter wave imaging radar kit. This works from 62 to 69 gigahertz, and we also do have this VR radar. Actually, this is one of the UWB radar kit that I have procured. Actually, this is we are going to have this 10 different models. We thought of having this antenna array for DO estimation. So you can see this is we can even include this in the we can even include this in the drones for short range surveillance. Okay. So we are establishing the problems, and we thought of going ahead with this proposed experiment. And you can see over here, this is ultra-wideband radar modules that we are going to have. These are the transmitting antennas. This is actually transceiver. Okay. Yeah. With this, I would like to conclude. We have HP 100 also. Our BTech students are working. Yeah, with this, I would like to conclude my presentation. I'll open to the discussion now. Yeah, if you have any queries, please let me know, so that
So audience, any queries? You can unmute yourself.
Hello.
yes, ma'am. Yes, please.
Sir, DOA and TOA, there are two concepts. So both are correlated with each other, or they have the different applications?
No, both are different, madam. DOA is nothing but the direction of arrival, where you are going to find out from which direction you are going to receive the signal, whether it is from. So that's the reason why we are going to divide the entire region into different angles, enter the space into spatial spectrum. We are going to plot at 0 degrees how much peak you are going to get, 10 degrees, 20 degrees. So this is actually considered the DO estimate. Time of arrival is going to estimate the time in the sense at what time you are going to have. Actually, this time is linked with the range estimation, how far the target is there. So both are completely different, madam. These two are, one is for range estimation and another one is for angle estimation.
Okay, okay. So in V2X, we can use TOA?
It depends. It depends. Actually, the time of arrival estimation, the objective is to estimate the range of the target. If in V2X estimation, in V2X environment, the target, the vehicle will be usually in motion. So yeah, when you are supposed to take the decision specifically for this driverless cars, driverless cars. What actually happens is the environment keeps on changes specifically in traffic environment, and you know what? Identifying the range, identifying the time of arrival, and identifying the direction of arrival, both are equally important because the time of arrival will help us to estimate the range of the target, whereas direction of arrival will help us to estimate the direction from which the other vehicle is approaching this particular actual vehicle. In the sense, if we are assuming that the driverless car is having the original car is traveling on the road, and some other car tries to overcome it from the left side or right side, both the time of arrival and direction of arrival both are equally important, madam.
Okay, okay. Thank you.
Any other queries, please?
Any other queries?
Sir,
Yes, please.
can you please distinguish between this angular resolution and range resolution? In angular resolution, you said about like the cars which are separated within a particular distance, right? So can I consider it as the distance can be detected using the range, whereas in angular resolution, like how to relate it, I don't know, sir.
See, I'll tell you one thing, madam. I have two targets. One is at 10 meters and another one is 10.1 meter. So if you are not in a position to resolve these two targets separately, you'll be getting only one echo signal. So one echo signal, the radar takes the decision that at some 10 meters distance, one target is there, because the resolution capability of that radar is very poor. So that's about the range resolution. So when it comes to the angle, that means 10, see, it is irrespective of the angle there. So 10 meters range, it can be of 10 degrees or 20 degrees or 30 degrees, whichever be the angle, it is not material to me, because range resolution never bothers about the angle of the target. Whereas in the angular resolution, range is not at all a problem. So whether it is 10 meters distance or 10 kilometers distance, I don't have any problem. But whether both are coming in the same beam or two different beams, that matters to me, because if it is in the same beam, only one echo will be coming, and hence the radar will say that at this particular angle, it will be some 10 degrees, we are having one target. But if the beam width is very, very narrow, in the sense that these two targets comes under two different angles, it again depends upon the beam width of the antenna. Both are completely different, madam. Angular resolution, time resolution, this range resolution, both are different. Angular resolution depends upon the beam width of the antenna. Range resolution depends upon the bandwidth of the antenna.
Okay, sir. Okay. Sir, one more question. You talked about this covariance matrix and correlation matrix, right, sir?
Yes,
so if it is covariance matrix, the search area will be from means minus infinite to infinite, right? So whereas in correlation, we will be having a specific bounded search area.
See, I'll tell you, I don't know where it got missed. Ultimately, in DO estimation, the such a space is fixed. Whether you would like to do it from minus 90 degrees to plus 90 degrees, or minus 60 degrees to plus 60 degrees, that this is actually the spatial spectrum. Spatial spectrum plotting from minus 180 to minus 90 to plus 90. When it comes to the covariance, actually what we try to do is we try to calculate the covariance in specifically in music algorithm to estimate how the variables, these random variables, the received signal is getting affected by the other things. We calculate the eigenvalues for this covariance matrix to estimate the angles. One disadvantage of music algorithm, I already told you, we need to know how many number of targets are there. Based on that only we can able to find out the corresponding signals. If it is two targets, only those particular eigenvalues and corresponding eigenvectors will assume, and then its corresponding angle we'll try to consider.
Sir, have you considered only the bounded search space then?
Yes, bounded search space only will consider.
Sir, can you please tell me the approximate cost of the radar you have shown us?
So the millimeter wave radar, it is actually we took the suggestion from TCS research. It is something around 3.4 lakhs, I think. But the other one is a little costly, that ULB radar. Maybe if you approach me, I'll try to share you the details. But my advice is, if you're really interested, just try to utilize the resources that are available over here, because it is a little worthwhile. The ultra wideband radar. Maybe after my 10 years of research, I struggled a lot to procure that thing. Anyway, we will surely share it, because it's the government organization at NIT Andhra Pradesh. I will surely support you. Many people, I have seen, many people are working in the ultra wideband radar, but specifically for through the wall radar imaging and many other applications, indoor communication. Okay.
Okay, sir. Thank you. Thank you very much, sir.
Thank you so much, madam. Any other queries, please?
Sir,
Yes.
how short distance and how long distance we can detect means vehicle when target is coming?
Usually, madam, when it comes to the defense application, the range is very large. In the sense, the transmitting power is also huge, and intercontinental, because the missiles or the aircrafts, enemy aircrafts, it will be kilometers away. But when it comes to the vehicular communication or V2X case, there's direction of arrival estimation. The basic motive is just to specifically in a driverless car situation, to avoid these collisions. So the ranges are not too big, too large. Actually, hardly it will go. But you know what? At the same time, the minimum range also is there. You see, to avoid the collision between two vehicles, specifically in driverless cars, at least we need to maintain some 1 feet or 2 feet distance. So otherwise, the chances of getting collision is very high. So this you might have observed this thing, the radar guns that are being used for measuring the velocity, speed of the vehicles, specifically on the highways. So hardly it will be some 250 to 300 meters. 300 meters, or let us assume 500 meters, half kilometer. So before maybe beyond that, your radar gun also will not work. That is used to estimate that velocity of the speed. So yeah, in vehicular communication, the ranges, I don't think it will cross more than 500 meters.
500 meters. Okay, thank you, sir. And sir, there is one more concept of Doppler sheet. So whether the moving target can affect this part?
Certainly, madam. That topic I haven't included over here. In vehicular communication, specifically because of the motion, the signal Doppler frequency, the return echo Doppler frequency is getting affected a lot. So that is the reason why estimating the channel is very, very difficult in a vehicular communication, because the environment keeps on changing. So yeah, in that situation, usually people go for delayed Doppler domain representation. OTFS is being used to convert this delayed Doppler domain channel. And yeah, surely in DO estimation is getting affected by that. But if you properly estimate the channel, specifically in delayed Doppler domain, yes, there is a chances of overcoming the difficulty in estimating the direction of arrival in fast moving environments.
Okay. And sir, one more thing. In one of the slide, you have mentioned that we have considered two targets. Okay.
Yes.
So in this vehicle communication, how many maximum vehicle we can what we can say correlate or detect like a target?
See, as such, whether it is a DO estimation or range estimation, the number is not at all a matter. See, resolution is actually the important thing. See, if my resolution is good enough, two targets which are very close to each other, if I am in a position to distinguish, that is really a good, that's the benefit for the end user. See, number of targets can be any. See, but your radar should be in a position. See, again, I'll take the example of this radar gun used on the highways. So if this particular radar gun, if it is in a position to detect the three vehicles, we need to have three different speeds. Which speed has to be displayed in which direction, that we need to estimate, right? So, and one more thing is, if both the vehicles are coming in the same line, then the problem arises, whether that speed is of the the one which is coming in the first, or the speed is of the second one which is coming behind. So again, the resolution comes into picture over here.
Okay.
Understand, madam?
Okay, okay. And sir, last question.
Yes, please.
Are you allowing us to visit your institute, or whatever the things you have shown means for some experimentation or under some research work you are
Yes,
allowing?
yes, madam. Yes, you try to drop an email, and yeah, we will surely, because it's a government organization, we cannot say no. We can, because even the government is also opening up all the equipments available for the citizens of India who want to do some work. They can book some slots and then make use of it. But the point over here is, first we should understand the fundamentals of this, how to operate this, and how to because see, if we don't know how to operate and then start working, then I don't think it is good. So initially some training might be required, but that will.
Okay. So you are providing training also?
See, we have recently procured it and we are doing experimentation, madam. So
Okay.
hopefully, in a way,
Okay.
if you want to
Okay.
come and visit, yeah, you can come and visit, and maybe along with my research scholars, you can come and sit, do some work, and I can surely go for the publication. That's after
Yeah.
acknowledging the institute. That's the different thing.
Okay, okay. Surely,
The
sir, I
gates
will
are open,
connect
madam.
with you. Yes, yes, I
Yes,
will
sir.
connect you. So thank you so much. So nice session.
Thank you so much, ma'am.
Any other queries, audience?
I'm sorry, sir. I don't know whether I have taken more time or less time.
No, sir, no, sir. Shall we conclude, sir?
Yeah, with your permission.
So, on behalf of organizing committee, I extend my sincere gratitude to our distinguished speaker, so Dr. Puli Kishore Kumar, sir, for sharing such valuable insights into the fusion of advanced signal processing and neural network techniques for V2X applications. Your talk has deepened our understanding of intelligent communication systems and their real-world implications. I also take this opportunity to thank all the participants for their active involvement and passionate listening. So thank you all. Thank you, sir.
Yeah, thank you so much, sir. I'm dropping my email ID over here, sir. If anyone is interested, they can.
Share, drop, sir.
Yeah. Thank you so much for giving this opportunity, sir. Once again, special thanks to you, sir.
We have to thank, sir, actually. Thank you, sir.
Actually, you adjusted my slot also. I need to thank you.
It's our duty, sir.
Thanks a lot, sir.
Anyway, thanks a lot, sir.